Hello everyone and welcome you all for today's session. In our previous class we have discussed about turbulent and laminar boundary layer, and we have discussed some properties of boundary layers, and we have also discussed about boundary layer thickness. So now how boundary layer properties can be defined by various parameters. So today we are going to discuss these parameters which are used to calculate boundary layer thickness and displacement thickness, momentum thickness, energy thickness, shape factor, and skin friction coefficient. These are parameters these are parameters which are used to discuss properties of boundary layer. And let us recap from the what we have discussed in previous class. So let us again discuss in short. So this was a boundary layer. This was a boundary layer over a flat plate. This was a flat plate, and fluid is coming from free stream velocity, that is a x component of velocity, that was a u naught was free stream velocity. And here we have discussed boundary layer formation of boundary layer here. So let us discuss foundation of boundary layer. Initial boundary layer formation from H was laminar, and here after some distance turbulence transition created, and then it become turbulent. So that was a boundary layer, and we have started from x equal to 0, and this was a transition started at around 3 into 10 to power 5 Reynolds number, and it was completely converting into turbulent at 5 into 10 to power 5. So this was a transition zone where disturbance started, because initially velocity is not very high when flow is coming over this plate. So initially velocity, same image you will find here, both side of the surface, same boundary layer will form. So this is just same mirror image you can see here. Initially flow was laminar, means viscous forces are dominant here, and here inertia forces also becoming significant. So turbulence started here, and up to that point when Reynolds number reaching 5 into 10 to power 5, flow completely become turbulent, and now velocity reaches in such a way that along this direction, when moving along this direction x, more and more fluid velocity increasing, and also viscous dissipation also increases. So this boundary layer thickness increases along direction of x. When we move along direction of x, boundary layer thickness also increases, because turbulence also causing more dissipation. So velocities will be affected, and velocity is slowing down up to this point. Suppose we are reaching up to this point and we draw profile here at distance x, but when in turbulence zone, even in turbulence zone, flow is not fully turbulent. This turbulent zone never touching the surface of the boundary. This thin layer of this is known as a laminar sublayer. This is known as a laminar sublayer. Laminar sublayer means even in fully turbulent region, starting from here and beyond this, though flow is fully turbulent, but still there is a flow within this boundary layer. We see that this flow within this boundary layer is a thin layer over the surface, where viscosity and surface effect is more prominent, and flow is completely laminar. But beyond this layer is very, very thin. Beyond this, flow is fully turbulent. So boundary layer increases when we move upward in y direction. When we move upward in y direction, boundary layer increases. Boundary layer increases in y direction. This boundary layer increases in y direction. If we draw a velocity profile here, you will find velocity profile like this. This is a velocity profile, and this boundary layer, within this boundary layer over the surface of this plate, flow is stagnated. Means it is always less than what is a free flow. Here you can see beyond boundary layer, and this is a zone, which is highly viscous. There is no exact line where we can say this is a fully turbulent flow and here is free flow. So this boundary layer, this boundary is fictitious. So how we can say that what is the maximum velocity that reaches, that is equivalent to free? So here we define that up to this point. Suppose at this distance this velocity is becoming this u. When this u become 0.99 up free stream velocity, then we can say it is a boundary layer thickness. We define boundary layer thickness by defining that velocity up to this point at distance x from leading edge reaches 99% of the free stream velocity. So this is a way we define boundary layer thickness. This is a boundary layer thickness from free surface. That is a you see that this is a plate, and from leading edge at distance x, we up to this point of the boundary layer we reached 99%. Means fluid velocity at this point particle of fluid will have velocity 99% of the free stream velocity u naught. So at that point thickness of boundary layer is boundary distance from the surface to the boundary, this boundary layer is known as a boundary layer. This is where we can define boundary layer thickness. Other parameters that we are going to define are, but this boundary layer thickness, here you can see flow properties are defined by Reynolds number, purely by, because here up to 3 into 10 to the power 5 beyond before this it was totally laminar, and this is because Reynolds number is not high, means flow velocity is not so high. That's why here flow is laminar and profile is parabolic. And beyond this, velocities are increasing, dissipation are also increasing, turbulent features are also increasing. So here this is known as a transition zone from 1 to 2. This is a transition zone. Here velocities are increasing, and up to 5 into 10 to the power 5 flow is fully turbulent at higher Reynolds number. So here we are again when flow become fully turbulent, means Reynolds number is increasing and inertia forces overcoming viscous forces, and more energy losses also takes place when we move from x equal to 0 to higher distance. And that's why region of influence of this surface where flow is affected by this boundary of surface, it increases and reaches maximum at this point. That is and beyond this flow become fully turbulent. This is where we define boundary layer thickness. Other parameters that we are going to define are number 2, displacement thickness. Number 2, momentum thickness. Number 3, energy thickness. Number 4, shape factor defined by H. Number 5, skin friction coefficient. That parameter we will also define skin friction coefficient, CFX, that is equal to displacement thickness divided by momentum thickness theta. This ratio, all the parameters are outcome of this boundary layer, means due to this stagnated flow within this boundary layer causes displacement thickness, momentum thickness, energy thickness, shape factor and skin friction coefficient. So why displacement thickness? Because we know that due to this boundary layer formation, fluid velocity within this boundary layer is stagnated, means below the natural velocity u naught. So this means that actual flow flowing through within this boundary layer is less than flow would have been flowing when in absence of this surface. In absence of this surface, more fluid would have been flowing from this region. So due to this formation of boundary layer, this fluid loss of fluid is shifted beyond the boundary layer. So how much fluid is shifted that would have been flowing in absence of this boundary layer is calculated by the displacement thickness del star. It means loss in flow of the mass within boundary layer is shifted beyond the boundary layer. That we have to define on the basis of boundary layer thickness. So let us define here. Again we will define, this is a velocity profile, draw a tangent here, and here velocity is, because we define boundary layer thickness del at velocity reaches u equal to 0.99 u naught, u equal to 0.99 u naught. So this is shifted, means this shifting is taking place. Suppose this shifting is equal to del star. Due to this, at boundary layer thickness, fluid is not flowing from this region to this region, fluid is from this region to this region, from this region to this region, fluid is not flowing in actual amount that would have been flowing in absence of this boundary layer. So how much fluid is flowing? Because here velocity is here beyond this boundary layer thickness, velocity become u naught. So let us see that this thickness is del star. This thickness is del star, and width of this plate perpendicular to this board is b is a width of the plate. So suppose at distance y, if it distance y from the surface, of the plate, we take layer dy thickness, and here velocity is u, and you know the full velocity is u naught at this point. So remaining is u naught minus. So how much fluid is flowing through this strip of dy thickness? Mass of fluid flowing through rho is density of fluid, and dy is width of this strip. Quantity of fluid in strip dy thickness. How much quantity of fluid is in strip dy thickness? That is equal to rho dy, b is width, and velocity u is velocity. So that is a amount of fluid in kg. You can say mass. This amount of mass is flowing through this strip, and there is loss, because if there is a velocity u naught, because in absence of, how much loss is taking place because of this boundary layer. So loss in mass flow equal to rho b u naught dy, because in absence of boundary layer, velocity would have been u naught, so actual minus rho b u dy. If it is actual mass flow, this is in absence of the boundary layer, this amount of fluid is rho b u naught dy flowing. But due to formation of boundary layer, this amount is flowing. So net loss, how much net loss of the mass is taking place? That is equal to rho b u naught minus u into dy. This loss of mass occurring in this thickness only. So total loss of mass is, how much total loss will take place from this point to this point? How much total loss is taking place from this point to this point to this point? In absence of the boundary layer, how much loss is occurring? Because due to presence of boundary layers, this amount of loss is occurring due to this strip. So total loss will be equal to integration of this value from this point to this point. So total loss in mass flow equal to integration 0 to del rho b u naught minus u into dy. This is a total loss of mass. Due to formation of boundary layer, this loss is occurring, and this loss of, so this quantity that is lost due to formation of boundary layer, now how much thickness of fluid is beyond this boundary layer is flowing, that will compensate this loss. The loss of fluid flow occurring due to this boundary layer and shifted over this boundary layer. So how much thickness of the fluid is shifted beyond this boundary layer having velocity u naught. So let us define by del naught. Equivalent loss, equivalent mass flow beyond boundary layer means this loss of this mass flow due to formation of boundary layer shifted over the boundary layer, that is a del naught thickness. So how much fluid that equate with this mass? That is equal to rho b del star u naught. That will be equivalent to loss in mass due to formation of boundary. So both are equal. So rho B del star U naught equal to 0 to del rho B U naught minus U dy. Now rho B can be replaced because these are constant, and del star equal to 0 to del 1 upon U naught minus U dy. That is equal to 0 to del 1 minus U upon U naught dy. That is equal to del star. Displacement of the this is known as a displacement thickness, means fluid is displaced beyond the boundary layer, equal to loss in mass. This is thickness of the fluid. This is thickness of the fluid beyond the boundary layer. That is equivalent to total loss in mass due to formation of this boundary layer. So this represents thickness of the fluid layer beyond the boundary layer, which is equivalent of the fluid that is lost between y equal to 0 to y equal to del. Y equal to 0 because of formation of this boundary layer. This amount of fluid was lost, and it is compensated by the thickness of the boundary layer, thickness of the fluid beyond the boundary layer, that will equate. So this is equal to this one. It is very, very important concept of the displacement thickness, because mass is displaced beyond the boundary layer due to formation of the boundary layer. Next one is momentum thickness. If mass is displaced, then momentum will also displace, because equivalent momentum equal to mass into velocity. If mass is displaced, the momentum will be displaced and energy will be also displaced. So next one is a energy displacement. So first equation that we have derived, momentum thickness, that was equal to, here momentum thickness was del star equal to 0 to del and 1 minus U upon U naught dy. This is a displacement thickness. Second one is a momentum thickness. So again we start from the loss in mass flow. Momentum of fluid. First mass of fluid flowing through this strip. Mass of fluid flowing from strip layer dy equal to rho B dy into U. And momentum of fluid in absence of boundary layer. What is momentum of fluid in absence, and what is momentum of this fluid? So again you can find momentum. What is momentum of fluid? Momentum of fluid of same fluid. Momentum of same fluid. Rho B dy U into U, because mass into velocity, that is equal to rho B U square dy. This is momentum of fluid. And momentum of fluid in absence of boundary layer. Momentum of same amount of fluid in absence of boundary layer, because in that case velocity of fluid will be U naught. So momentum of fluid in absence of boundary layer, BL, that is equal to rho B U dy into U naught, that is equal to rho B U naught into dy. Loss in momentum due to formation of boundary layer. So loss in momentum, and within this thickness, within this strip only, loss in momentum, that is equal to, subtract from this one, this is equation number 2 and this is equation number 1. Subtracting equation number 1 from equation number 2, because this one larger. So rho B dy common and U common, that you will find U naught minus U. This is loss in momentum because of this step only in this step. Total loss in momentum we have to indicate from 0 to del. Total loss in momentum, momentum equal to integration 0 to del rho B U common U naught minus U and dy. This is equation number 3. So this is total loss in momentum due to fluid is displaced from the boundary layer. So that amount, this will be denoted by the theta. Momentum is denoted by the theta. So let us, it is theta equal to theta. This is now thickness is theta. So what is momentum of the fluid flowing in theta thickness of the fluid beyond the boundary layer? So find this momentum. That will be equivalent to total loss in momentum. Let us define here total loss in momentum. Momentum of fluid within in thickness theta, that is equal to rho B, rho B is rho B and del rho B theta. B and theta is area, then multiplied by U, then mass U naught, and again we multiplied by U naught because we have to find out momentum. So that is equal to rho B theta U naught square. This momentum, that is a fluid of thickness theta shifted beyond the boundary layer, that will be equal to total loss in momentum due to formation of boundary layer, equating both. So rho B theta U naught square, rho B theta U naught square equal to 0 to del integration rho B U naught minus U dy. Now replacing constant and finding theta. So theta equal to 0 to del integration U upon U naught square U naught minus U dy. Now balancing, taking U naught, taking one U naught outside and one U naught inside. So we get 0 to del U upon U naught 1 minus U upon U naught dy. This is a momentum thickness. Momentum thickness means a loss in momentum due to formation of boundary layer within this boundary layer is equivalent to the theta thickness of fluid flowing over beyond boundary layer having this momentum. Now what is thickness of the momentum? That is known as, this theta is known as momentum thickness. This theta is known as the momentum thickness. Theta equal to 0 to del integration U upon U naught 1 minus U upon U naught dy. This is a momentum thickness. And now third one is a energy thickness, because when mass is shifted beyond boundary layer, momentum loss is occurring. So energy loss will, momentum and energy both are related to each other. So what is the energy loss? So first we find out energy loss in a layer of thickness dy. First we found energy thickness in layer of the. Third one is the energy thickness, that we define by, here energy thickness we define by del star, double star, because already we have defined displacement thickness by del star. So now define energy thickness by del double star. So first we find what is the energy of this fluid flowing in this strip. So energy, same energy of fluid, energy of fluid in a strip dy, that is equal to rho B and dy, rho B dy, and U is the mass, and multiplied by U square by 2, because energy is 1 by 2 mv square. So that is a 1 by 2 rho B dy and U q. And energy of fluid in absence of boundary layer. The boundary layer is not there. What will be energy? What would have been energy of this fluid in this layer? So energy of fluid, loss in energy of fluid in absence of boundary layer, that is equal to 1 by 2 rho B U dy, that is mass, multiplied by U naught square. So loss in energy due to absence of, loss of energy in this strip due to presence of boundary layer, loss in energy of this fluid within this strip due to formation of boundary layer. So loss of energy equal to 1 by 2 rho B U common, we can take U common, that we find U naught square minus U square, and this loss of energy will be displaced by this theta thickness. So total, this is, and total loss of energy, total loss in energy, that we integrate here 0 to del 1 by 2 rho B U naught square minus U square, that is common. So how much this energy compensated that fluid is shifted beyond the boundary layer? So that thickness is del double star. So loss in that we can calculate here. Energy of fluid, how this total loss in energy is compensated by the energy of fluid flowing with thickness del double star. So shifted fluid energy in thickness del double star, that is equal to 1 by 2 rho B del double star is the thickness that is it now volume, and this is become mass, and u naught multiplied by mass, u naught is become mass, and then multiplied by velocity u naught square, that is equal to 1 by 2 rho b del star u naught q, and this one is equal to loss of energy due to formation of this boundary layer. So equating both 1 by 2 rho b del star u naught cube equal to 0 to infinity, 0 to del 1 by 2 rho b u naught square minus u square. So again replacing constants here, and we now equate. So del double star here del double star equal to 0 to del and u upon u naught cube u naught square minus u square. Simplifying this one, 0 to del u upon u naught 1 u naught square upon u naught square minus u square upon u naught square. This will be replaced. So that we get 0 to del u upon u naught 1 minus u square upon u naught square and dy. So this one is a third equation, that is a energy thickness. All these equations you can see are very symmetrical in nature, and you can easily remember to use these equations. So let us now writing all these three equations at one place. So this one, third one is a energy thickness. Energy thickness del double star equal to 0 to del integration u upon u naught 1 minus u upon u naught whole square dy. These are three very important relations, and most of the time you will find in a good GATE examination and IES engineering service examination to solve question to find out momentum thickness using these relations. You will given whenever you find that this value will be given in questions, this value will be given in question, this value will be given in question, and you have to find out by these relations you can find out a different thickness. Another point is remaining here, that is defined as one parameter h parameter, that is known as a shape factor. This is known as a shape factor that is equal to a ratio of displacement thickness to momentum thickness. Displacement thickness to momentum thickness means you can here put here value 0 to del 1 minus u upon u naught by 0 to del integration u upon u naught 1 minus u upon u naught dy. So this is a shape factor. This you will always find a number, not a you find dimensionless number. This is dimensionless number. You will always find. Next one is that is skin friction coefficient CF. Skin friction coefficient CF. It is a ratio of wall shear stress to dynamic pressure, because when fluid will flow over the surface of the object, it will create skin friction. And wall shear stress is known as a tau naught, means shear stress is maximum at the wall surface. So this ratio is known as a tau naught upon 1 by 2 rho u naught square. That is because at velocity, dynamic pressure is equal to any velocity will be there, u naught square, free stream velocity or some other velocity will be there. So but tau naught is a wall shear stress, that is maximum over the surface of the wall. So this ratio is again is a dimensionless quantity. So this I think this one was not dimensionless, because displacement thickness and momentum both are different quantities. So this is not dimensionless, but this one is a dimensionless, because both having same dimensions. This is a dimension of pressure, and this is also dynamic pressure. Dynamic pressure means Newton per meter square, Newton per. This one is a dimensionless factor. These are very important terms, and for further analysis of the boundary layer in turbulent region and momentum equation, we will use these parameters, and these will help you to understand nature of the boundary layer and nature of fluid friction occurring over the surface of the object. Thank you very much, and next class we will solve some questions based on the formation of, because these questions are very the only thing that required basic knowledge of integration. Because integration, if you are weak in integration, you can't solve this question, because in momentum thickness you can see square terms are appearing, and again u by u naught and multiplied by this one then become cube. So cubical equations you have to integrate. So integration, for integration purpose you have to revise integration so that you will easily solve these questions. These questions are very easy, but one thing that you have to have practice of solving integration. Thank you very much for watching. Please share and like and subscribe.